Assalamualaikum warahmatullahi wabarakatuh and very good afternoon. This week we begin with the first topic, which is topic number one, Introduction to Electrical Systems. Here are the lessons that we are going to discuss in this first chapter. We'll begin with a small introduction on the generalities of electrical systems. So what are the main components of electrical systems, and how do we use certain vocabularies to describe electrical systems? And then we'll look at the what we would say fundamental element that makes electricity, which is electric charges. So we'll discuss a bit about the origin of electricity. We'll talk about electric charges and the movement of electrons that create that currents. And then after defining that, we will go directly into defining several, as you mentioned in the title, the most important parameters in electricity. The first one would be the current. So we'll discuss about current flow in the circuit, and then we'll discuss about what we will call as you usually know it as voltage, but the proper term that we might use to call it is basically is either electromotive force (EMF) or potential difference. Both of them are, we might call them as voltage. And then after defining all those terms, we'll look at the electrical units that we in SI units, the units that we use to quantify currents and voltages, or EMF and potential difference. And then we'll talk a bit about Ohm law. So it's a law that you might be very familiar with. And at the end, this might not be done this week, but this is something that we're going to also discuss on resistors, different type of resistance, and is coding for particular type of resistor. So let's begin now. So as introduction, we already know that electricity is basically one of the essential parts of our life today. And in terms of engineers, we need to really know when we talk about electricity, there is a specific domain or area that we're talking about. We're not discussing like a scientist. For example, scientists, what they do is they seek to understand and propose an explanation to the phenomena related to electricity. But we are not going to discuss at that level of fundamental, where we try to explain behaviors in electricity. As engineers, what we do is basically we take benefit of that explanation, or when we say explanation means we take benefit of the laws that have been addressed by the scientists, and we use it to basically all those properties, we use it to turn it into a useful application. So we use those laws to make calculations and to create useful applications. So in terms of electrical engineers, we might find four categories of engineers. So this is also correspond to the larger area of electrical engineers, right? So it can be ranging from production of electrical energy, so where you create that source of energy and store it probably, and then we transmit the energy, so this transmission of electrical energy from the production to the user. And then there are engineers that dealing with applications of electrical energy, so converting that electrical energy into a usable form of energy. For example, mechanical, converting electrical to mechanical, or converting electrical to heat or even light. And then finally, of course, there are very specific groups of people who study the control of electrical energy. This means basically trying to manipulate the way that the electrical energy is transmitted or distributed to the user. Before we goes into the details of basically studying the circuits and the terms related to electricity, you might wonder, where does our electricity come from, right? So our electricity today that you have as you turning on your laptops and turning on your lights or your fan or your air conditioning system, they basically comes from what we call generating station. So they are operated by electricity supplier. So in Malaysia, we have for example, the largest one is Tenaga Nasional. So what do we have basically at our generating station is we have multiple huge turbine that convert kinetic energy into electrical energy using what we call generators, right? So basically what happens is they mostly burn natural gases and coal. So they heat water, turn it into steams, pressurized steam, and then the steams will rotate a turbine, and then the turbine basically rotate a generator, and that generator convert the mechanical energy from the rotation of that turbine into electricity. So that's where you have your electricity. So as we can see in the graph over here, is basically the origin of electricity generated in Malaysia. Most of them are either come from natural gases, from well, natural gases and mainly coal, right? So we are very quite far from all renewable energy, and of course it's your job in the future to do that. So what happened next is that that energy, when it is generated, so here we have a category of engineers that works into on energy supply or energy generation. Then it is transmitted through transmission lines. So like you can see in this figure over here, you are most surely familiar with these transmission lines all through the country, right? So it transmits energy from the generation system to the end user. So end user might be there might be different categories, right? Houses and industries. So they transmit it at different level of what we call voltages. And then after that, we also have instead of using energy directly coming from generation from the power station, we might also use portable energy, like what you have in your handphones or in your laptops. So they have also been charged using energy generated in the power station, but they can be stored. So that's what we call as batteries. And batteries, usually you have two types of battery, either primary cells or secondary cells. So the difference are just being rechargeable or non-rechargeable, right? So that is quite a common form of energy storage. So you store it for later utilization of an onboard utilization, we would say. So where does electric circuits come from? Electrical circuits basically comes into picture when there are needs to basically properly utilize the available energy. So the energy that comes from the grid or comes from your battery need to be converted into a proper level. Let's say we'll use the term right now, but we'll look at it later, into a proper level of voltages and currents that can be fed to the application. So for example, in your phone, that can be fed into the transmitter for communications, can be fed into your screens to light up your screens, and so on and so forth, right? So there are plenty of electrical circuits in our electrical or electronic devices that convert the energy that comes from the battery, or in case of appliances at home, comes from the power supply from your socket on the wall, to convert it into a form that is more suitable for your appliances like your washing machine, your TV, or your food processor. So as we can see just now, basically we can chunk down, or we can separate electrical system into four main elements. The first one is source. So source is where you provide the energy or you generate the energy. So it could be battery, generator, or socket outlet on your wall. And then there is what we call a load. So source is where energy comes from, where energy is stored, and where energy is come from and delivered. And then you have load on far right. So load, what is defined by load? So it's specific term in electrical. So load is the component that consume your electrical energy. So for example, it can be your home appliances, like I mentioned just now, washing machine, TV, lamps, heaters, or even in other applications, industrial application, it could be motors to operate your pumps, your computers, and so on and so forth. And then in between the sources and the load, so there are plenty of electrical circuit. In between, you have the transmission system. Transmission system is basically the part that deliver power from your source to your load. And then finally, you have what we call control. Control is basically a part of circuit as well in between that manage and control the energy flow and distribution in the transmission. So there are elements and circuits like switches, contactors, switch gears that you operate in order to control the power flow from the source into the load. So if you look into a more practical point of view, let's say we take something that is more simplistic. Imagine if you have in a room that has no wall socket, you need to supply a certain electrical energy, for example, to light up the rooms. So in order to light up the room, you need to have a lamp, and then the lamp need to be supplied by electricity, and the electricity could come from, for example, from a generator. So a generator like your pasar malam generator, right? So it's operated by diesel, and then it rotates a certain I'm sorry, not diesel. So for example, it's a small petrol engine that rotates a certain turbine, which is the generator, and then the generator produce electricity. So the power supplies come from generator that supplies power to the lamp, and of course in between you have some sort of switches to control the energy delivery, whether you want to switch it on or switch it off. So we would say in a phrase, we say that a generator supplies a lamp bulb. So a generator supplies a lamp bulb. Lamp bulb is the load with a switch to turn the lamp on or off, right? So in a schematic diagram, we could draw something like this, where we have the source, which is the generator on the left that supplies voltages, we will say, and current, of course. And then on the right side, we have what we call the load. So the load here is the part that consumes the electric energy. Here we have the bulb. And in between, you have, of course, the switches that close or open the circuit to allow the power to be transmitted from the source to the load. So the wire is basically the transmission system. So there you go, in most simple simplistic form, you have all the four elements of power source, load, control, and transmission, right? So there are different symbols related to all these components. So after having basically discussed about the generalities of the components of an electrical system, so now let's talk about the origin or the fundamental elements that make all possible, right? So basically what happened in your wires of conductors when you supply energy from your power sources to the load, what happened is there are electrical charges that are circulating in your conductors. So energy is basically transmitted due to the movement of these electrical charges, and therefore we need to have basically more or less several basic understanding on electrical charges. How do we measure them, and how do we measure them, I'm sorry, in electrical engineering. So what is electric charge? Electric charge is basically an excess of negative or positive electricity on a body or in a space. So in simple term, if we there is two types. If we have an excess of negative charge, it is called negative charge. If we have an excess of positive, it is called positive charges. So positively charged and negative charged bodies are mutually attracted, and similarly charged bodies repels, right? So that's, I think, a properties that you know about charges. So the question is, where does these charges come from? So these charges come from, of course, from it is part of the atom. So in atom you have, for example, you have electrons, which is the elementary particle that is negatively charged. So an electron is negatively charged. Proton is the elementary particle that is positively charged. And then we have neutron and proton build the nuclei at the middle of the atom structure, and neutron is neutral, right? So an atom usually have the same number of electron and proton, but the electrons can, however, be added or taken away from the atom. It makes the atom a charge, or we call it as ion. So an excess of electron, it becomes a negatively charged atom, we call it as anion, and an excess of proton, it becomes a positively charged atom, we call it as cation. So when we have that free electron, we can have a movement of those electrons, and those electrons carry negative charges, right? So free electron at the end of the atomic structure can move around. So every electron, when they move, they has a certain potential energy. So imagine it's like in mechanical, you have potential energy if you climb into a certain height, mgh, or you have a potential energy, you have a certain energy that is called kinetic energy when it moves. It is the same thing. So every electron have potential energy, and it's in a suitable medium. If it has a medium that is suitable, the electrons can move freely from one point to another point. And this electron, that is charged, these charges, what it like to do is basically it like to move from a higher potential energy to a lower potential energy. So it is true for everything. For example, in fluid mechanics or even for a mass, what happen if you put, for example, put something at a certain height, it has a higher potential energy, but when you release it, it will fall down to the earth. Why? Because it want to go to the point of lower energy. So the same thing goes for charges. When they are placed at a place which is at a higher, has a higher level of energy, and they are connected to a point where there is less energy, what they would like to do is would like to move from that high potential energy to a lower point of energy. So this transfer of electrons occurs in a medium that's what we call as conductor. So conductors such as copper, aluminum, or silver. And there are of course elements on the opposite that doesn't allow the flow of electron. That is what we call as insulators. So I think you all knows about this already in physics high school, right? And there are also another element that we call semiconductors. Semiconductors basically is the element that have both properties, a mix of both properties, can sometimes be conductors and can sometimes be insulators. So when we have those potential energy that I explained just now, the charges will start to move, and that's what we call a current. So current, what is current? Current is basically a flow of electrical charges, when there are charges that moving around in your conductor. That's what we call a current. So in order for current to flows continuously, so you have a source basically is like a tank of charges that has on one terminal high potential energy and the other terminal lower potential energy. That's why you have in your battery basically plus terminal and negative terminal. So what do they means is basically plus means you have an excess of energy, minus means lower point of energy. So when they are connected, they are connected, what happens is that the charges want to move from high energy to lower energy. So they move inside the conductors, and when they go through a load, they will basically operate the loads. So for example, if it is a bulb, it will light up the bulbs, and the bulbs will consume the energy of the charges that is delivered by the, for example here, by the battery. So in order for current to circulate, so what we call now, here we go, the terms of electrical current. In order for a current to circulate, what we need, there is two conditions. The first one is that there must be a potential difference. Potential difference means between these 2 points over here, there need to be a potential difference. There need to be a difference of energy level. And then second condition is that there must be a complete circuit. So the point of different potential need to be connected. So in this case, for example, over here is connected by the wires, and there is a load in the middle. So just now we talk about the difference of potential, right? So difference of potential that create that current. So it is what we call as electromotive force and potential difference. So both of them are usually, you know it as voltage, but we need to distinguish sometimes the terms between electromotive force and potential difference. So what is both of them are basically voltage. So what is voltage? Voltage is basically the difference of energy between 2 points. So if you take a circuit like this, when you take 2 points, you compare the level of energy. The difference of that level of energy is what we call voltages, right? So in any 2 points across the circuit, you can measure a voltages. But if you measure the voltages across a source and the voltages across a load, it has different names. Technically, it has a specific different names. If you measure the voltages across a source, that's what we call electromotive force. So electromotive force is basically, what does it name electromotive force? It's somehow represent the force that wanted to push the the charges to move, right? Because in battery, that's what you have. You have a certain level of energy that's pushing the charges to move out. If the circuit is connected, then the force will push the current to move. Whereas for a load, for example, a resistance or a bulb, it is what we call just as potential difference. It's not an EMF, we call it as potential difference. Why? Because the load basically consumes the energy of the charges that come into it, and then at the end of it, what happens is the energy becomes smaller. So imagine if we have a certain amount of energy that comes into here, After it goes through across the load, what happened at the energy at the end here, it will be much smaller, and the difference of the energy is what we call potential difference. So now across the load there is a potential difference. So you can read the explanation over here, but in general that's what it means. So if all energy is transferred to the load unit, for example in this circuit, if you only have one EMF, one battery, and one resistor, that should mean that the EMF, the voltage across the source, will be equal to the voltage across the load, right? And both are quantities that is measured as voltage in volts. So there is a certain convention. A voltage or potential difference is a vector quantity. When we talk about a vector quantity, means it has a certain direction. We indicate a certain direction. Usually what we do is we indicate the direction using an arrow. A lower point of energy, we start the arrow, and at the end of the arrow, at the point of arrow, it is basically the point where we have a higher level of energy. So the arrow somehow indicates basically the level of energy. For example, the EMF over here, we have the direction upwards because we have lower level of energy at the bottom and higher level of energy at the top. So for load, now you can imagine the arrow is basically need to be lower point of energy at the bottom and higher point of energy at the top, because energy arrives at the top. So the direction of the arrow for the voltage across the load is the same as in the source, right? But if you go through the circuit in following the current flow, the direction of EMF and direction of current flow is the same. Why? Because at the point of higher level of energy, the charges will come out of it. So the direction of current flow is in the same direction of the EMF. However, when compare the direction of current flow, so here in blue is the arrow pointing out the direction of current flow. If you look at the load, the direction of current flow is in opposite direction of the voltage on the load, right? It is on the opposite direction of the voltage on the load. So that is the convention or the standard that we use when we indicate the voltages and current, right? So that is here the explanation. Why do we have such conventions? Because current flow leaves the source at positive terminal, so we call this positive terminal, right? So we have a high level of energy and it circulates into the load. Now it still has the same level of energy, but when it go across the resistance, it gets to lower level of energy. So that's why we have these two arrows of voltages of EMF and potential difference in this direction, while the direction of current flow in the direction to the right as shown in the figure. So potential difference is also called as voltage drop in certain textbook. They means they're basically the same thing. Now let's talk about the units. So we have different units. We talked just now about currents and potential difference or EMF. So a current is measured in ampere. So 1 ampere is basically 1 ampere has a very specific definition. So the definition is quite complex. It is basically related to a certain force, because we know there is electromagnetic magnetic force properties on a conductor that's carrying a current, but we're not going to explain that because we need to have a certain background on electromagnetism. But I want to know is that just that the current is measured in ampere, and it is easier basically to understand currents in relation to charges, the quantity of charges. So charges that we call Q. So for example, in electrical units, what is charges? Because we want to understand current just now, we need to relate it with charges. So charges is basically the SI unit for charges is in coulomb, noted as C. 1 C or 1 coulomb of charges represent an excess or deficit of 6.24 times 10 to the power 18 of electrons, right? So if you have an excess or deficit of 6.24 10 to the power 18 of electrons, that represent 1 coulomb. So what is the relation between Q and I? 1 1 coulomb of charges is defined as the quantity of charges passing a point in the circuit when a current of 1 amp is maintained for 1 second. Okay, so if you have in a conductor, imagine it now, you have a conductor. So inside that conductor, what happened is that there will be charges moving. So that's what current is, right? So if you have 1 ampere of current, so you measure it, you have 1 ampere of current for 1 second, that represents 1 coulomb. So in terms of equation, charges Q is basically the product of current and times. So if you look at, if you want to know what the definition of current, so coulomb is just a quantity of charge, it's an amount of charge. What is current with regards to charges? Current is basically, if we isolate current, we can bring times to the other side. So current is the ratio of charges per second. So current is basically the quantity, the amount of charges that flowing through a conductors per second. So it's what we call as flow rate. A current means how many charges flows inside the conductors per second, right? Charges, a current and in ampere represent the amount of charges that's circulating in a conductor per second. So you have, for example, this kind of exercise that you may try in your slides. So I really encourage you to try it out. So for example, here, for example, if a charges of 25 coulomb passes a given point in a circuit in a time of 125 milliseconds, determine the current in the circuit. So imagine 25 coulomb charges for circulate for 125 seconds in a conductor. What happens is, if you want to calculate the current, we know that amount of charges is the current multiplied by time. So the current is basically the ratio of quantity of charges per time. So how many charges per time, that's the current. So the current here is equals to, for this value, equals to 200 amps. So the more charges that circulates per second, the higher the current. So when we look at something that has high current, it means a lot of charges flow through the wires per second. Low current, for example, a low current compared to 200 amp, if we consider 1 amp, 1 amp means we have a smaller amount of charges that circulate through that same circuit or same conductor. And then let's see about voltages. What is voltages or potential difference U? What is the unit? And how is the unit defined? So the SI unit is in volt. And how do we define 1 volt? 1 volt is defined as a potential difference between 2 points of a conductor that dissipate power of 1 watt per 1 amps current withdrawn. Okay, in simple words, let me explain. So imagine if you have a load or an element. You pass through it 1 amps, right? And then you measure, you pass 1 amp, and then you want that 1 amp to provide 1 watt of energy, 1 watt of power dissipated. So if you pass 1 amp through the load and it produces 1 watt of power dissipated, the potential difference across that load is defined as 1 volt. So voltage is basically the ratio of power divided by current. So it's how much power that you need in order to circulate a certain amount of current. So voltage is basically a quantity of power per current, and there is also another form of it, because we know what is power. Power is basically work or energy over time, so we can write it as work over time. And current, as we see just now, current is basically charge over time. So we can write it as, so it's at the bottom, so it's the inverse of it, so T over Q. And we can cancel out T, so it becomes W over Q. So voltages is also an energy per charges. So what is voltages or potential difference? Voltage or potential difference is amount of power to move a certain amount of current, or in other words, is the amount of energy that you need in order to move a certain charges. Okay, so it is a form of energy that you need to move the charges around. So that's what we call voltage. So imagine if you have a battery of 1.5 volts compared to a battery of 9 volts. 9 volts means you have more energy to push a certain number of charges, whereas a 1.5 volt only have a smaller amount of energy to push to push the same amount of charges. So that's what it means as potential difference of voltages. So here we have another example of question related to the potential difference of voltages. So the question asks, if a circuit delivers an energy at the rate of 20 watts, so rate of energy is basically power, so 20 watt means 20 joule per second, energy per second, so that's what we call 20 watt, and the current is 10 amps. So imagine it delivers a power of 20 watts. So don't be confused with the term energy at the rate. Energy at the rate means energy per time. So energy per time is basically power. So this is power, not energy. So it delivers a power of 20 watt and the current is 10 amps. So energy dissipated 20 watt when you circulate a current of 10 amp. Determine the energy of each coulomb of charge in the circuit. So what it needs to know is, so we know that there is current circulating, so the charges circulating inside the element. They want to know for each coulomb of charges, what is the energy level that goes through the circuit. So what is the strategy? The strategy is, of course, to go through voltages. We know there is a relation between power and currents. We know that voltages is basically the ratio of how much power per amps. So we can calculate voltages. And if you want to know the quantity of charges, we know that voltages can also be written as a function of charges, because what is voltage? Voltage is also, as we seen just now, is also the ratio of energy per charges. So let's see how we solve it. So first what we need to do is to find the voltages. So it's just power per current, 20 watt given divided by 10 amps, that gives us 22 volts. So the energy that is the potential difference across that element is 2 volts. So now the question is, what is the energy per charges? So energy per charges, we know that voltage is energy per charge, W over Q. So W is basically the voltage multiplied by charge. Okay, voltage is 12 volts. What is the number of charge? They want to know for one charge, for each coulomb of charge. So you just multiply it with 1 coulomb of charge. So for each coulomb of charge, 1 coulomb of charge, the energy of that 1 coulomb of charge is basically 2 multiplied by 1, which is 2 joule. Right? So let's go to the last units, basic units of electricity, which is the resistance. So the SI unit of resistance is ohm, with the symbol omega, Greek letter omega. So what is this? What is defined by 1 ohm, quantity of 1 ohm? So 1 ohm is basically is defined as the resistance between 2 points of a conductor. So imagine you have a conductor, and you take 2 points. So in between these 2 points, when 1 volt is applied, so when you apply 1 volt of potential difference, right, and it results in 1 amps of current circulating. So voltage, if you apply 1 volt of voltage, potential difference. So what is potential difference? Potential difference is amount of power per current, right? So you apply 1 volt and it circulates in it 1 amp of current. So the resistance inside that particular element, we call it as 1 ohm. So that's the definition of 1 ohm. And the relation between them is basically the voltage or potential difference is resistance multiplied by the current. So U, or you might call it as V, but I prefer to write it as U because V you might be confused with the units volt. So U, or potential difference in volt, equals to the resistance multiplied by I. Right? Following the relation between current and charges, we can also write, therefore, U equals to Ri, of course, and P equals, so power, because you know what is power. Power is basically voltage per current. So its power is IU. So if you replace basically U by IR, you can get power P equals to I square R. So in this form, power equals to I square R. This is the form that we call it as the emphasis on the energy dissipated by the current. So a resistance, a load that have a certain resistance where we circulate a certain amount of current, we create a certain energy. We'll emit a certain amount of power P, right? So in relation to that resistance, basically there is the Ohm law that can be defined, or that was found, that led to the definition of resistance. So Ohm law was found by George Ohm in Munich in 1827. So what happened is basically he set up when he has a test specimen like this, where he has a certain power supply, a voltage or EMF that is connected to a certain resistance, and he measures the current that goes through the load or the resistors and the voltage across that resistors. He found out that the potential difference, so PD is the potential difference, the potential difference across the conductor or across this specimen of conductor, resistor, is proportional to the current. This has a certain condition at a constant temperature. So what happened is that he set up this experiment. We has a certain conductor connected to a power supply, so a voltage supply. And basically what happened is that he varies the value of voltage supply. So as voltage varies, he remarks that currents also varies proportionally. So voltage is proportional towards the currents, and that coefficient of proportionality is what we call today as resistance. Okay, so a constant potential difference over current characteristic is what we see in this figure over here, and this is the circuit from which it could be obtained. So here there is a question related to Ohm's law. So the question is not very straightforward. It is a bit tricky. It needs you to go. It is a question that's related to a certain application that needs a certain strategy for you to think about. So the question says a motor gives an output power of 20 kilowatt. So imagine there is a motor that output the power of 20 kilowatt and operate with an efficiency of 80%. So 80% means if you put into it 100% of energy, at the output it will only produce 80% of that energy. So there is 20% that is loss into heat, basically. If the constant input voltage to the motor is 200 volt, what is the constant supply current? Okay, so imagine the 20 kilowatt motor that has an efficiency of 80%. If it is supplied with 200 volt, what is the current circulating in it? Okay, so the first thing that you need to do is, of course, we know that if the power at the output is 20 kilowatt, 20 kilowatt means 20,000 watt, we have to find first what is the power in the input. So power input has to be higher than 20 kilowatt because we have efficiency at 80%. So basically what you need to do is just to divide the power at the output by the efficiency. You'll find out a higher power of 25 kilowatt. So this 25 kilowatt is basically input is produced by an electrical input, right? It's produced by an electrical input. So imagine you have a motor. You need to put into it an electrical energy, and in output it produces mechanical output, right? So the mechanical output is 20 kilowatt. So because it has a certain efficiency of 80%, you need therefore to supply more than 220 kilowatt. So that's where we get this 25 kilowatt, 25,000 watt. And as we've seen just now, power in electricity is basically the product of voltage by current, right? So if we know that it's a product of voltage by current, now we can deduce what is the current by dividing the power with the voltage. So 25,000 or 25 kilowatt divided by the voltage of 200 volt, it gives us a current of 125 amps. So the things that may not be straightforward is basically related to the efficiency. So you need to know that a device, any device, electrical device, it has an input energy, which is electrical in this case, and it has an output energy. In this case, a motor is basically, it gives an output of mechanical energy, right? So that's how you solve it using Ohm law. So there is another example that is a bit more complex, that need basically a certain background in mechanical engineering, calculating energy as well in mechanical. So you may try to do it. It's not that difficult. but you have to pay attention to the steps properly. You need to calculate the energy of a moving train that has a certain weight of 200 tons. So you can follow through the explanation one by one. I hope you try it on your own. So that's we are almost at the end of this week topic, discussing about electrical parameters, basic parameters of current, voltages, and resistance, and a bit of Ohm law. So another thing that you need to know is that in terms of circuit condition, there are two important circuit conditions that you need to identify. I mean, not need to identify, that exists, that you may be found in at a certain moment, right? So we have looked at Ohm law just now. So Ohm law is the case where there is a proportionality between current and voltages, and the proportionality coefficient is basically what we call resistance. And in terms of that value of resistance, we may have two extreme condition of value of resistance. So we may have a value of resistance that is extremely high at infinity value, or extremely low, close to zero. This is two specific configuration. So if we have the resistance at a very low value, so let's say it's very close, 10 towards zero, if you look at a U equals to IR or U equals to RI, if you have if you supply the circuit with a certain voltage sources, like a battery, for example, and if you have your resistance close to zero, it means there is no resistance at all. The current can circulate freely. And if you look at the equation U equals to IR, if your voltage supply is constant, and if you have your R close to zero, then it means your I will get it will shoot up to a value towards 10 towards infinity, right? So it means in your circuit it will be in this condition where you have no resistance at all, where your all the charges inside your source can circulate back into the lowest point of energy as fast as possible. So that means you have an infinitely high amount of current, a very high current. That's what we call short circuit. So short circuit means basically when you have no resistance and all the currents goes back to the negative terminal, or the low potential, low energy point. So you have a high current, and this high current basically can cause a lot of heat and burn your circuits. So this is what we call short circuit. Short circuit, when you heard short circuit happens when you have your resistance close to zero, right? Your resistance close to zero. And when you have false contact, for example, with the ground, where all the current just flow directly to the ground of point where the energy is very low. And then on the opposite side, what you have is when you have your resistance extremely high, close to infinity. So if you look at the same equation, U equals to IR, or I equals to U over R in another sense. If you have your R extremely high, you will have your current that tends toward zero, right? So if R very high tends toward infinity, then your current will tends towards zero. So if it tends towards zero, it means that no current that can circulate in it. So it is similar to this case where we have what we call an open circuit. Just now it's short circuit, now it's open circuit, where current cannot circulate and there will be no current at all. This is what we call a condition of open circuit. So we can model it by, we can basically model it as an open circuit where 2 points are conducted by infinite resistance, for example air, where air is a very high, is basically an insulator, extremely high electrical resistance, so no current circulating. It is an open circuit, right? So here are the summary of a few important concepts and a few important relationships or equations that you need to know. So what is current? If we can summarize, current is basically the rate of flow of electrical charges, how many charges per second. So I equals to Q over T, or in other way, charges is a current multiplied by time. So a source supply energy to a system, a load accepts energy and consumes the energy. So electric charges may be positive or negative. So this is related to charges. So to maintain current, the source must provide a driving force called EMF. So this comes from the source. So it's a potential difference across your source, like your battery. Potential difference across a load indicates in voltage is the energy loss per coulomb, so how much energy per charges in order to move that charge across the circuit. And since the current is rate of flow, its product with the voltage give the rate of energy transmission, which is power. So if you multiply current with voltage, that is what we call power, right? And resistance is a measure of opposition of flow. So it's how hard it is in the material to circulate current or circulate charges. And Ohm's law finally state that ratio of voltage over current, U or V over I, is constant, and that's what we call a resistance of the element. So here are the equations that you need to I would say learn by heart, or if you understand the concept, you won't be able to have a problem at all to refine it. For example, current is quantity of charges per time. Voltage, what is voltage? Voltage is power that you need to supply a certain current per power per current, or energy that you need to move charge, so energy per charges. And Ohm law says V equals to IR or V equals to RI, so it's the proportionality between voltage and resistance. And there's another one, power is the product of voltage and current. So that's all for this week. Thank you very much. I really appreciate you attending the session just now, and hopefully you will have a nice session with the tutor tomorrow for the tutorial. Please download the question and try to do it during the tutorial with your tutor together. Thank you very much. See you again next week. Thank you.